Starting off here, example 8. How many of the following derivatives could you answer correctly? Take 1 minute and find out. Try these 4 derivatives out. I'm going to guess you're going to get tricked on at least maybe 2 of them, but maybe not. Try them out. All right, so if we are looking at these, letter A, the derivative of e to the e, well, e is just a number. So if I take the derivative of a number to a number, the derivative of a number is 0. Okay? This is my favorite derivative because it stays the same. The derivative of e to the x is just e to the x. Now, x to the e, I bet most of you guys got that right, because you will use the power rule for this, because e is just a number. So if it was x squared, the derivative of x squared would just be 2x, right? What is the derivative of x to the e power?
E times x to the e minus 1.
There you go. E times x to the e minus 1 power. All right, these are all of our options that you think, and you are all wrong. Sorry. You said x to the what?
X to the x squared minus x.
X to the x squared minus x. Still incorrect, I'm sorry. Okay? The reason is, you guys, because technically I have kind of 2 things going on, right? I have this x and then I have an x up top. So that's not just a number, so I can't just use the power rule, okay? So let's think about if I wrote this as a function, y equals x to the x power. Here is where our log properties come into play, because if I have an exponent up top and I want to move it down in front, I can take the log or the natural log of both sides, right? So I could take the natural log of y, and that's equal to the natural log of x to the x power. That allows me to now move this x that's in the exponent down in front. And now could I take the derivative here? Yeah, I can take the derivative of this. This is where that implicit differentiation comes into play. It allows us to differentiate things that we can't actually solve for y, right? So, and it allows us to solve things like when we've got exponents here as well. So I'm going to take the derivative of the natural log of y, which is equal to 1 over
I don't think we remember a log
y.
property.
Huh?
I don't think we remember a log property because we haven't been using them.
I know you haven't been using them, but most of you guys had Mr. Eitzen last year, yeah? He would be so sad to hear that you forgot some of your log properties.
He'd understand.
He'd understand?
He knows where
I just don't remember this word.
Yeah, that's fair. So the natural log of y, if I take the derivative of that, it's just 1 over y. But since I have y and I'm taking the derivative with respect to x, I would also be multiplying this by dy dx. Okay, and then on the other side here, I've got 2 things. I've got x times the natural log of x. So I'm going to have to use what? The product rule. So I've got the first one times the derivative of the second one. Derivative of natural log of x is just 1 over x. And then I'm going to add the second function, natural log of x, times the derivative of the first function. Okay. Again, we're trying to find the derivative with respect to x. So I'm solving for this thing right there. Okay. So let's simplify this here. X divided by x on the right-hand side, that gives me 1. Plus the natural log of x. On the left-hand side, I still have the 1 divided by y times dy dx. Now, how do I get the dy dx piece by itself? Yeah, just multiply it by y, right? Times by y. So we have dy dx is equal to 1 plus the natural log of x times y. Now, if I go back to the beginning, what was my y equal to? X to the x, right? Y equals x to the x. So for y, instead of writing y, because I want this derivative with relation to x, I'm going to write times x to the x here. So the derivative of this function, x to the x power, is actually 1 plus the natural log of x times x to the x power. There's no other way to do it other than using your log properties and applying that applying the product rule in order to solve. Yeah. So again, this part D we could not solve using the differentiation rules that we know. So if this happens, if you have a variable in the exponent, you can use logarithmic differentiation, which is just using your properties of logs in order to rewrite it so that you can actually solve for your derivative. Okay? All right, next page. We got 2 examples. All right, I want you guys to find the derivative using that same idea that we just did of y equals x to the 2x power. Okay, so think to get rid of this 2x in the exponent, we have to take the natural log or the log of both sides. Does it matter which one I use? Nope, they both do the same thing. So I can take the natural log of the left and the natural log of the right to get us 2x times the natural log of x is equal to the natural log of y. So go ahead and take the derivative of both sides. You will still have to do the product rule on the right side, and then solve for your dy dx. Okay, we'll go over it here in a few minutes. Okay, if I take the derivative of the left-hand side, I get 1 over y times dy dx. On the right-hand side, I leave the 2x. I take the derivative of the natural log of x, which is 1 over x. And then I leave the second one alone, take the derivative of the first one, is 2. And now I can simplify this and solve for dy dx. So dy dx is equal to 2 plus 2 natural log of x. How do I get rid of that dividing by y? Multiply it by y. So I need to multiply this whole thing by y, which I don't want to leave it in terms of x and y on the right-hand side. I want to leave it in terms of just x. So I would rewrite this as dy dx equals 2 plus 2 natural log of x times x to the 2x. Okay? There you go. So on your flashcards, one of the derivatives that you wrote on there was anything like y, if I have y equals a to the x, the derivative of that is just a to the x times the natural log of a, right? That's like using the formula. Now, if you saw this problem on like a test or an AP test or something like that, and you're like, I have no idea what this formula is, and I don't remember how to find the derivative of that, you can use that idea of logs to help you find the derivative of it, okay? Just like how we kind of were able to derive some of the derivatives of like the tangent, the cotangent, if I rewrote it in terms of sine and cosine, that kind of stuff. There is ways to derive it with using the log differentiation. So if I wanted to solve this using log differentiation, I would take the natural log of both sides, and I would have x times the natural log of 2 on the right. And then you would take the derivative of both sides again, right? So if I take the derivative of the left, I get 1 over y times dy dx. And on the right side, I technically have just a number times x, right? Isn't natural log of 2 just a number? So if I had just like the derivative of 5x, what's the derivative of 5x? 5, right? So the derivative of the natural log of 2 times x is what?
0.
Not 0. The natural log of 2. Because the natural log of 2 is a number, right? So that number times x, the derivative of that number is just the natural log of 2. Or sorry, the derivative of that thing times x. All right, and then I get derivative by itself. So dy dx is going to equal the natural log of 2 times y. But y actually equals what? 2 to the x, right? So I'm going to replace that with y. So I've got the natural log of 2 times 2 to the x is equal to the derivative with respect to x. Okay, so again, that's the same thing. That's what the formula says. But if you forget what the formula is, you can just use the differentiation of logs to solve it. Okay? All right. Example 10 here. Find the derivative of this function using log differentiation. Okay? We could we not technically, what am I doing here? I could still find the derivative of this using quotient rule, right? But it'd be like quotient rule and chain rule all combined and stuff. So you could do it that way. I'm going to show you also using the log differentiation. We got to remember our log properties, however, though. So the main one here is when I divide using logs, what operation am I using? Subtraction. So I'm going to have, actually I should probably take the natural log of that side And then the natural log of this side would be x minus 2 squared minus the natural log of, I'm going to write it as x squared plus 1 to the 1/2 power. Okay, I'm going to rewrite them so that those powers are down in front. So this becomes 2 natural log of x minus 2, and this becomes 1/2 natural log of x squared plus 1. Okay, rewriting it with logs now allows us to solve the derivative, taking the derivative of both sides. All right, so now I can take the derivative of the left side would be 1 divided by y times dy dx. Now on the right-hand side, the derivative of the natural log of that stuff is just 1 over that stuff, right, in parentheses. So the derivative of 2 times the natural log of x minus 2 would be 2 divided by x minus 2. We okay with that? Yeah. Okay, then I've got minus 1/2, and the derivative of the natural log of x squared plus 1 is 1 over x squared plus 1, yes, in parentheses there. Okay, however, this one on the inside, don't I need to use the chain rule there? Take the derivative of the top there. So the derivative of x squared plus 1 is also 2x. So I took the derivative of the function, the outside function, and then take the derivative of the inside function of 2x.
So how did you get the second one?
So can I go ahead and cross out these 2's here? Yeah. And then I've got 1 over y times dy dx is equal to 2 divided by x minus 2 minus x over x squared plus 1. And last thing we got to do is just get rid of that y. So I'm going to times by y on both sides. So we've got our derivative with respect to x is equal to our fractions subtracted. And then all of that is being multiplied by y. And my y is actually this whole thing of x minus 2 squared divided by x squared plus 1 underneath that square root. Okay. So in this lesson of differentiating inverse functions, okay, we're going to find 3 different ways to find the derivative of an inverse. Today we're actually going to only look at 2 different ways, and part of your homework is going to be trying to figure out what the third way is. So we're going to look at these different ideas of how to find inverses and look at derivatives. If you guys remember from pre-calc, from your wonderful pre-calc teachers, inverses, a few things about inverses. If I have a function, f of x, the inverse function is denoted with the little -1 symbol, right? That is my inverse function. Now, the domain, which means my x values, and my range of my function, how do they change when I go to my inverse function? They flip, right? My range actually becomes my domain, and my domain actually becomes my range. Okay? What this means is basically just your x and y's are flipped, right? Which, if you think about this graphically, if I looked at a graph, for example, if I had the function x squared, actually, let's just do the right-hand side of x squared. If I had something like that, my inverse function looks like this. It's not perfect there, but it's flipped over this line, y equals x. right? All of the x values, all of the x values on our black equation will be the y values on the blue equation, okay? So we are going to find the derivative. Given our function, we're going to find the derivative of the inverse, okay? So the first ways that we're going to do this is we are just going to actually find out what the inverse is and take the derivative of that, okay? But sometimes that's not going to be able to work like that, so we have to have other methods to solve, okay? So method one, easiest method, is when you are given an equation and you can find the equation of the inverse, we can just take the derivative of that, okay? So here's your 3 little steps. Find the inverse, take the derivative, and then plug in your point wherever it says to evaluate it at, okay? So example 1, I've got f and g are inverse functions where f to the negative 1, so the inverse of x is equal to g of x. If our function of x is equal to x cubed minus 1, find the derivative of 7, okay? So note here that this g prime is actually, I need to find what the inverse function is, and I'm taking the derivative of that. Okay? So, in order to do that, I know that my original function is y equals x cubed minus 1. If I wanted to solve this for my inverse function, what would I do? Switch the x's and the y's. Okay? So this becomes x equals y cubed minus 1, and I can solve this for y. So I get that y equals the cube root of x plus 1. Okay, so this is technically my inverse function. So just be careful when you're writing your notation here that you don't write the wrong thing. Remember when I was first doing derivatives and I was teaching inverses in pre-calc, I was writing the wrong thing. Try and be careful when you're writing what is your inverse and what is your derivative. So this is my inverse function of x is equal to the cube root of x plus 1. Okay, but now I want to take the derivative of that. Okay, so I need to take the derivative of the inverse. Do we see that notation there? The derivative of the inverse is how you say that. I could rewrite this as x plus 1 to the 1/3 power. Do you agree? Okay, can you take the derivative of that? Yeah, let's take the derivative. I get 1/3 times x plus 1 to the negative 2/3 power. Okay. Now, if there's anything other than just the x plus 1 in there, and I had like x squared plus 3x, I would also have to take the derivative of the inside. But there's just x plus 1. If I took the derivative of that, I would just get 1. Okay? So this is the derivative of my inverse. Now it's saying that we want to evaluate it at 7. Okay, so all I'm going to do is I'm going to plug in 7 here. Okay, so this now becomes 1/3 times 7 plus 1 to the negative 2/3 power. Which is the same as 1/3 times 8 to the negative 2/3 power. Which is the same as 1/3 times the cube root of 8 squared, right, in the denominator. So this would equal 1/3 times, what's the cube root of 8? 2, and then 2 squared would be 4. So this is 3 times 4, which is 12. So I have 1/12 is the derivative of my inverse. So algebraically find the inverse by switching your x's and y's, and then take the derivative of that function after you've solved for y, okay? All right, let's look at this next example. Find the derivative of the inverse function of x at x equals 3. So I've got here that y equals e to the 2x. So if I wanted to find the inverse, that means I switch my x and my y. But now I need to solve for y. How am I going to solve for y? natural log, right? So I'm going to take the natural log of x is equal to 2y times the natural log of e. And the natural log of e equals 1. And to get y by itself, I'm going to divide by 2. So my derivative, or sorry, my inverse is natural log of natural log of x divided by 2. Which you could think of that's the same thing as just 1/2 times the natural log of x, right? Right? Same thing? So now I have the inverse. I want to find the derivative. So I need to find the derivative of that function. Well, what's the derivative of natural log of x? 1 over x, right? And this coefficient, just that number, stays with it. So it's actually going to be 1 over 2 times 1 over x, which just equals 1 over 2x. So that is my inverse derivative function. And if I'm evaluating at 3, I can plug in 3, and I get 1 over 6. Does that make sense? Yeah? Okay. Let's look at method 2. Okay, method 2, you will need to use a calculator for this one. And we will stop after this one, so you guys will have some time to work on your homework. Okay, so this method you are going to use when finding the inverse is difficult or impossible. AKA, there is multiple y's, and you cannot solve for just y. You'd have like y times some other y factor, right? So I can't just get y by itself. So when we're solving for our inverse here, we're still going to flip our x's and y's, okay? But we're not going to solve. It says don't solve for y, okay? We are going to take the derivative of both sides of the equation, which is why that implicit differentiation from last class comes in handy, because I'm going to have to take the derivative of things that have y with respect to x, okay? So then we're going to solve for dy dx just like you guys did on your homework. And that is going to be in terms of y, and then you're going to plug in your needed y value. But we might need to solve for our y value originally, okay? Because, well, I'll get to that here in a second. I don't want to overload you with info until we start working on it. So this example 1, I've got a function, f of x equals x cubed plus 2x plus 1 at x equals 1, okay? So that means my original function is just y equals all of that stuff. So I've got y equals x cubed plus 2x plus 1. If I want to find my inverse, I'm just going to switch the x's and the y. So x equals y cubed plus 2y plus 1. Okay. Can I solve this for y? No, because there's 2 terms that have y in it, so if I factored it out, it would not work out. So what I'm going to do is I'm going to take the derivative of both sides with respect to x. So on the left side, what is the derivative of x? 1. On the right side, the derivative of y cubed would be 3y squared times dy dx. Derivative of 2y is 2 dy dx. Okay, now just like last class, we want to get the dy dx by itself, so I'm going to factor out dy dx to give me 3y squared plus 2, and that equals 1. So my derivative is equal to 1 divided by 3y squared plus 2. Okay, so that implicit differentiation allows us to take the derivative of those hard to solve for functions. However, on those previous 2 examples, all we did was then plug in whatever x equaled. However, now I have y. So that's a little bit of an issue. So what we're going to do is we're given an x value, right? Oops, we're given the x value of x equals 1. We are going to plug that back in to this equation right here to solve for what my y value would be in my inverse function, okay? So I'm going to set, it was 1, right? Yeah, 1 equals y cubed plus 2y plus 1. So now, if I looked at this equation, what is y going to have to equal? 0. This one's pretty easy to see. On the next one, I will show you how to use your calculator to actually solve it as well, if it's not easy to see like this, okay? So my y value is actually 0. So I'm going to plug in 0 in for my derivative function here of my inverse to give us 1 divided by 3 times 0 squared plus 2, which just gives me 1/2. Okay, so we found the derivative of the inverse. That's what that dy dx was. But then I was given an x value. It said x equals 1, but I need to have a y value to plug in. So I plugged in my x equals 1 in for my inverse function to solve for the y. Okay? The tricky part where people get messed up is they want to plug the 1 in for the function. Okay? I want to know what is the y value when x is 1 of my inverse, right? So I got to plug it into the inverse function to solve. Okay? All right, let's look at the next one here. Okay, find the derivative of the inverse function of f of x equals e to the x plus the natural log of x at x equals 3. So we start out with, I'm going to write it as y equals e to the x plus the natural log of x. Then I switch my x's and y's. So I've got x equals e to the y plus the natural log of y. Again, is there a way that I can solve for y here? No. So we have to take the derivative with respect to x of both sides. Okay, so I'm going to give you guys a minute. Try taking the derivative of both sides with respect to y and solve for dy dx. Okay, if you're stuck, ask the person next to you or ask me. I can come around and help. Okay, so derivative of the left side, derivative of x is 1. Derivative of e to the y is e to the y times dy dx. Oops. Now, derivative of the natural log of y, 1 over y times dy dx. Okay, now I can factor out that dy dx, and when I factor it out, I get e to the y plus 1 over y. And this all equals 1. So then we get dy dx is equal to 1 divided by e to the y plus 1 over y. That is my derivative of the inverse function. Okay? But now we are looking at when x equals 3. Okay? So I'm going to go back to my original inverse function, which is x equals e to the y plus natural log of y, and I'm going to plug in 3 for x. So I've got 3 equals e to the y plus the natural log of y. Now, is there any way that we can solve that? No, which is why we need a calculator. So in your calculator, I would like you in your graph for y1, go ahead and plug in the left-hand side of the equation of 3. On the right side, you're going to plug in the equation e to the x, because it's going to freak out if you put y, plus the natural log of x. Okay, so in your y1, put 3. In your y2, put that function. And then we are going to figure out where are they intersecting. Okay, because where they intersect is the solution. So you want to find the intersection point. Section point. You hit second trace, and then option 5 is intersect. Okay, so figure out what is your coordinate point for the solution. So your intersection point that you guys should have gotten was the point 1.0744, comma 3, okay? Now, the thing that we have to remember is we got to be smarter than the calculator. The calculator is a tool, okay? So we actually plugged in x here because otherwise the calculator gets mad. So the answer for y is actually in the x spot. Does that make sense? So my answer for y is the 1.0744. So I'm going to plug that in where I see y into my derivative. So my derivative evaluated at 3 is going to equal 1 over e to the 1.0744 plus 1 divided by 1.0744. Which obviously we are just going to plug in onto the calculator. And when you plug it in the calculator, double check that you get the same answer as me, but you should get 0.259. Or depending if you round it a little bit differently, you might have gotten a slightly different answer, and that's okay as well. Okay? Questions on finding derivatives of inverse functions? Okay.